Here, the topic is, as I was saying, that if something is related to your object, if there is a difference in attenuation, then the contrast is proportional to the difference between the object's attenuation and the background. The greater the difference in attenuation between the object and the surrounding background, the higher the contrast of the image. Additionally, as the thickness of the organ you are imaging increases, the absorption also increases compared to the background, which increases the difference in attenuation, thus enhancing the contrast. So the contrast here, as we said, partly depends on your object, the organ you are imaging, and partly on factors like iodine or high density materials. If you have a high density material compared to the background, its attenuation relative to the background is significant, giving you high contrast in the image. This depends, for example, on whether you have something with a large thickness present and something with a small thickness, creating a difference in attenuation, which results in contrast in the image. The topic of the film we discussed is the same. For example, if I want to calculate the contrast for a specific organ, it's similar to what we often see in publications where they calculate the contrast for a specific organ. You always see this equation that tells you that this equation represents the calculation of contrast. For instance, if you are dealing with X-ray film, you need to work on the optical densities. The difference in the optical densities represents the contrast present. Now, if you are dealing with CT, you need to work with the CT number. So, when you take an ROI as a region of interest, the spirit of bit as a vision of interest, you will find that there is a numerical value for the CT number. For example, the CT number for the dye or the muscle has a significantly high value in comparison to the CT number of the other tissues present. When you perform the calculation of the contrast, you have, for instance, two objects. Let's assume that this physical object, which is the one with high thickness, is present, and you have the background here. For example, my object has caused absorption of light or other forms of energy, so the transmitted photos from it gave me a low measured signal, while the background did not cause any form of attenuation, thus giving me a high signal. The difference between these two signals, A and B, represents the visual contrast. The value you get, if you want to multiply it by 100, will give you the percentage of the contrast. Taking the ROI, region of interest, for example, my median CT number is 100. Then I look at the surrounding background attenuation, which is, for example, 50. So it would be 100 minus 50 over 100. For the 100 milliwatts, multiply it by 100 if you want it as a percent of the average, which gives you the contrast value or the contrast of the image. This serves as a quantitative assessment for you. Now, for example, if we assume the opposite, meaning that your origin has low density, then your CT number will have a low value and the background will have a high value. This density, if the Z number is high, will reflect. What does that mean? It means that this is A and that is B. So what is it? Minus B over A, meaning if its value is high, it doesn't matter to you. You always relate to the larger one. You always relate to the larger one as if you are seeing Ahmed and Hussein or Hussein and Ahmed. In the contrast between Ahmed and Hussein will differ if you say Ahmed and Hussein or Hussein and Ahmed. It's the same story. So the contrast here or the variation here doesn't matter whether it's the background of your legend or your object or vice versa, depending on the Z number. You might also find the Z number, for example, coming out with a low value. So if you take B here, you might find it coming out as minus. Then you start to ask me how this value is coming out as minus. I will tell you X, and I will say stay large for you. What is it? As we mentioned before, we have the attenuation coefficient and its dependence on, of course, we have two interactions that occur: proton-electron interaction and Compton interaction, and their dependence on the Z number, as well as Compton's dependence on electron density and energy. I may have clarified in a video. I shared with you the topic of electron density. Decreasing, energy increases the contrast, and the energy increases the contrast and increases the attenuation, thus increasing the contrast. An increasing difference in the atomic number between the two tissues you are contrasting will also increase the difference in attenuation and enhance the contrast. Additionally, an increase in density will also increase the attenuation and enhance the contrast of the image. So, if I have, for example, there is a second group, and here there is a coverage group, meaning there is something covering this second group. The transmitted photons here refer to the difference in transmitted photons between the two groups, like A and B. Will the ratio differ between them? It will differ. Now, if there is no part covering the object, the ratio will remain 1. Yes, the number of photons may vary if I increase the dose, but for me, the ratio will remain 1 because it covers both. It wants to tell you that this ratio does not have a distinctive interaction because the ratio between the photons present in both will remain the same. What does the scatter do in the scatter? If you increase the kV and the scattering, will it reduce the contrast or increase it? Of course, it will reduce the contrast. Why? Because when you increase the contrast, there is Compton scattering that will improve it. The increase in the number of photons that will be present. And when you calculate later what is present or what is between the existing ones, you will find that it has an effect on the image. How this part works, to understand it, means this. This is one photograph, and here is another photograph from a different angle. Now this image here has reduced the contrast present in the image, which is very clear with the contrast. So how did this additional happen? How did this part happen? So here I have two objects, one A and the other B, and I have 1,000 photons. These 1,000 photons are incident on these two objects, right? Okay, so object A absorbs 50% and object B absorbs 90%, which means 100 photons pass through object B and 500 photons pass through object A. That means if you take the log of what passed through and the 500 from the two objects, if you want to take the log of that. When we talk about log relative exposure, it means the log of the value of the number of transmitted photons. This refers to the term relative exposure, which is the log of the number of photons present. You take the log of 500 and the log of 100 and see what the values are. You will find that the log of 500 is 2 and the log of 100 is 2.8. So, 2.8 represents the difference between the transmitted photons coming from the two objects, which represents your contrast. That's great. If we as we said, T2 is the log of 500, and this log of 100 means the difference between them. What will the difference in the logs be? It will be 0.7. This amount represents the subject contrast that exists. All right, if you then proceed to do The scatter is now 50 photons for the 2H element, so consequently the total becomes 150. In this case, the 100 becomes 150 and the other one becomes 70. So when you come here, the ratio between the two signals, which is 150 to 270, means the difference in the log here will be 0.3, even though it was 0.7 before. So here is the difference between them. The difference between the two organs decreased from 0.7 to 0.33, which means there was a reduction in the contrast of the image. So, what is the result of this? It is due to the presence of scatter. How were they addressing this scatter? They were addressing it in the presence of a grid and by creating an air gap. Regarding the patient and the image receptor, we will discuss the solution to scatter, specifically the grid and air gap, as these are the two solutions available for the issue of scatter. I don't know if we should give a brief overview of them now, but we will talk about them later. Now let's continue with our topic concerning image quality. So, if we talk about the digital image receptor in digital imaging, since I mentioned that it is highly sensitive and can detect low levels of radiation intensity, it will consequently be sensitive to saturation. If someone asks you whether digital imaging addresses the issue of saturation, the answer is no. This is an ongoing problem. This issue arises because digital imaging itself is inherently more sensitive and has higher detection efficiency. So how could it not detect saturation? It does not address saturation and actually causes problems. So, the problem of scatter is an existing issue whether we are talking about imaging or skin in radiography. Improving contrast involves thicker structures, greater attenuation between the objects, decreasing the kV, increasing the difference in the Z number, and increasing the difference in density. So, reducing contrast increases scatter. And also, how about the air gap? There is no distortion between the two that exist for us. The distortion between the two will be 1. Pay attention to one thing. When you reduce the two, who is affected? 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 If you have a low density object, for example, inside the body, a high density object means an object that has a high density. If you have another object that is a high density object, you will find that if your imaging system has the ability to show it, for example, when we talk about X-ray, it has high contrast sensitivity. And when we talk about CT, it also has high contrast sensitivity. In CT, you get cross sections with very high contrast in the images and sections you take, unlike X-ray. So you'll find that in X-ray, if something has low density, it is hard to detect, whereas high density objects are more easily detectable. If you talk about CT, you'll find that this story is not present. You might be able to do detection with a device like CT because it is compared to the comparison with X-ray. Is it usually a significant amount, or is this typically a problem? Well, in general, silence might just be a wonderful sign. Let's simplify it again in a straightforward manner. I, at the present moment, have the film, and the film is with Dr. Hani. You want to calculate the optical density of this film. What do? Simply put, you get a light source. The light source emits light that is falling on the film, and you place a detector under the film to start detecting the transmitted form. So now you have two pieces of information. I note and I transmitted. Let's assume that I note is 100 photons, and let's assume the transmitted is 50 photons. Now, how was this value determined in this scenario? Why did it count 50? Why did it count 100? And why did it count 90? What is the basis for what is counted in this context? Based on the darkening of the film, the burning of the film, if today the color is bright, what does that mean? If the film is intact as it is, what does that mean for the transmitted photons that will pass through the film? Should they be few or many? The film is still transparent as it is. I'm not holding it at all. If we say that the color present here hasn't changed significantly, what does that mean? When you come to display it and place it under the film, indeed, certainly. Will there be many transmitted photons passing through it? Will there be many? 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 Will there be many or not? Will there be? Will there be many or not? Will there be many? Okay, Abu Siban. The more darkening increases, the more it allows transmitted photons in the dark part, right? What will happen to it? It will decrease, right? So for example, the part with optical density is 0, right? This can allow a transmittance of 100%. As the degree of darkening in the film itself increases, in this case, the percentage of transmitted photons or the permeability of this part for transmitted photons will decrease. So this story relies on the I note of the already known source of radiation. Let's assume it is 100 photons, and any transmitted photons, you take your detector and measure the light photons that will pass through here. In this case, you say that the transmitted photons came out to be, for example, 100%. So the I at any node, this is called transmittance equals 1. Now, the optical density is the logarithm. The transmitted value, which is essentially considered as being the inverse of I node over IT ratio calculation process itself, will also produce a certain specific result. Thus, optical density measurement is crucial in determining how much darkening has occurred on this particular film sample layer due to exposure conditions applied during testing procedures. In other words, it means that this part of said film can indicate precisely how much darkening occurred due specifically to a given exposure level encountered, the relationship between exposure levels experienced, and resulting optical density values obtained from measurements taken thereafter can then be established clearly through analysis processes involved herein, ultimately resulting in generating an informative curve like shown here. Subscribe to the channel. Here, for example, Dr. Hani, if you are giving, say, a milliampere in this part, do you expect that darkening will occur on the film in this area significantly? When I increased its strength, for example, to 4, the amount or degree of darkening on the film starts to increase. So, it keeps increasing the milliampere, and then it begins to see the relationship between this and that in terms of what happened in the film. It starts to analyze this to see the film itself based on the value here. It begins to observe when this amount of darkening occurred and at what exact values, for example here and here, which I call the area where the system experienced significant changes. Just a small change in the milliampere resulted in a significant change in optical density. You see, you change small values in this value and the other value, which are these notes. So this resulted in a significant change in contrast. You can essentially determine the sensitivity of your curve with it, but the densitometer, indeed, gives you the optical density. The sensitometer, in fact, allows you to derive the characteristic curve, so yes, as you know, that's correct. It's like you're saying that what you did is equivalent to the amount that reached the film, being very low. So how much is it? How will it be measured? And so on, right? It's like you. The film that you have here has different types of sensitivity and speed numbers. The speed number indicates your sensitivity. The higher the speed, the more sensitive it is to radiation. As we will see, for example, you have film A and film B here. The speed point here shows that at 1.5, you get a certain optical density, while the other one requires high exposure. So, to achieve the same optical density with this film, it means you need to increase the dose on the patient, for example, to reach the same result. All of this is in screen film radiography because we are all talking about it. I apologize for bringing up the topic of screen film radiography, but I feel that if I delve into this, digital is also sensitive to this. However, as I mentioned, I have, for example, screen film radiography that behaves like this, which is its HND curve, the characteristic curve. While the digital behaves like this, what does that mean? It means that I have a wide range. There is a comparison to make sure, just the film that is mine, this is what I can work with, but if I work below, I won't find what I call it. And if I work above, the image here is black. And the image here, while in the system, how much do you have? So the curve is like this. You can work as you know. That's why it can improve if there's a problem with the milliampere values. It can affect the operation, and it can do manipulation with post-processing. You will always find these questions or tricks present when talking about digital radiography. Does it get affected by scatter? Yes. it is definitely affected. I am talking about TLD, which stands for thermoluminescent dosimeter, and it has both advanced and normal types. The normal type is designed to measure X-rays and gamma rays, while the advanced type is capable of measuring X-rays, gamma rays, and also neutrons, which is particularly important in certain applications. This device is widely used in radiotherapy for precise radiation treatment, ensuring accurate dosage delivery. Additionally, it finds applications in radiology or nuclear medicine, where it helps in monitoring and controlling radiation exposure. For instance, in radiotherapy, it is crucial for treating cancer patients, while in radiology, it assists in diagnostic imaging. So, what is the question? We should not end up with a blank page.